Hey, hello to everybody. My name is Jordi Binefa, and I am about to show you what is PLCedu and how it can be controlled using Snap. Here, in this picture, we see just a category called IoT Vertebrae PLCedu that depends of this another category, and this category depends on MQTT library on Snap. PLCedu can be managed using a Snap. There is no need of Raspberry Pi, or using Python, where Raspberry Pi is required. In this presentation of today, we don't need Raspberry Pi. MQTT communication is going to be using microcontrollers Wi-Fi. PLCedu has some embedded components. Here we can see the view meter reading analog outputs, normally open red button, writing a digital input, and a potentiometer setting a regulated voltage between 0 and 10 volts. Industrial digital voltages can be 12 or 24 volts. For convenience, we're using here 12 volts. Industrial analog voltages are between 0 and 10 volts. Okay, but what is a PLC? According to Wikipedia, a programmable logic controller, PLC, is an industrial computer that has been ruggedized, requiring high reliability and ease of programming. At bottom left, there are a couple of pictures of PLC classrooms, typical at electrical vocational training schools. And at bottom right, there is a system using an Arduino-based PLC from Industrial Shields that I am using in one of my last projects. And what is PLCedu? PLCedu is a use case of IoT Vertebrae, trying to simplify the learning of PLC-based systems design. IoT Vertebrae, those green boards in the right picture, is a scalable system able to connect lots of digital and analog inputs and outputs at real industrial levels. That means 12 volts or 24 volts DC in digital inputs and outputs, minus 10 to plus 10 volts for analog inputs, and 0 to 10 for analog outputs. Raspberry Pi, that is shown here, is optional. Raspberry Pi is attached to IoT Vertebrae through its GPIO, like a big hat. It is convenient when using Python to program PLCedu. In today's demo, there is not Raspberry Pi because we are using HEAD's microcontroller's Wi-Fi connection. Snap uses its MQTT library to connect with it. MQTT is the most common protocol used in IoT communications. There are two types of communications between the head and the boards, I2C and CAN bus. I2C is a well-known protocol used by makers using Arduino or other microcontrollers. And CAN bus, also known as Car Area Network, is the protocol used inside any modern car. PLCedu saves students to deal with cables, and it is ready to use and connect to real industrial world. Connections can be made using crimped cables on these terminal blocks. Glossary of terms. Terminal blocks on top right are the digital outputs from DO0 to DO3. At the left of these digital outputs are the digital inputs, from DI0 to DI3. Terminal blocks on top left are the digital power supply, 12 volts in this case, but it could be 24, changing external power supply. And minus D is digital ground, and plus D is 12 volts. At the left part of the picture, there are embedded components. View meter, normally open button, and potentiometer. View for analog VT for button digital level, and POT is for potentiometer regulated voltage between 0 and 10, are connected directly to this terminal block. And terminal blocks at the bottom right, are analog inputs, in this case from 1 to 4, and these are analog outputs from 1 to 4. Okay, digital outputs. In the picture, there is connected to digital output 2, this one, and digital ground. In the real demonstration, we are about to use a big red LED. Here we see the block, the out, and this one is bit 2, bit 0, bit 1, bit 2. That means that this is the signal for this bit. The out is sending 4 bits of 4 values at the same time. Remember, 1 is 12 volts and 0 are 0 volts. And with the block the out bit, we are sending a value, 0 or 1, to only 1 bit. At the right, there are two Python scripts, one using the out and the other using the out bit. Digital inputs. In this picture, there is an external normally open button connected to digital input 1. When it is pressed, here there are 12 volts. When it is released, there are 0 volts. The in-bit blocks is a reporter block that reads the 4 inputs at the same time. The in-bit reporter block reads only one of the 4 inputs. At the right, there are two Python scripts, one using the in and the other using the in-bit. Again, digital inputs. But the difference is that we have connected this cable from this BT connector to DI1, and it's mainly the same, but the difference is that here we are using the internal red button instead of the external one. Analog input. In this picture, we see just the output of the potentiometer, that is a voltage between 0 and 10 volts connected directly to the analog input 4. Here we see just the reporter block in, then we select a channel between 1 and 4, and we read just the volts at that channel. Here there is a Python implementation, and the analog outputs, we are just sending the output of this voltage to this terminal block that is connected directly to the VU meter. Here in the block, we are sending just the channel. We are in channel 4 and a value between 0 to 10. In this case, it is the 7. And here there are a couple of Python scripts just using a out. Okay, how it works. This slide shows how the blocks have been made. For instance, setup MAC is setting the PLC's Edu MAC number and connects to MQTT broker. This is just a block from the MQTT snap library. Here, for instance, the in reporter block is just calling another block from IoT vertebrae. And inside this block, we see the use of the MQTT snap library. The other PLC Edu blocks are based on IoT vertebrae blocks too. Now we're about to do a practical demonstration. You can download this presentation and you have a direct link from here. And now I am just connecting to the PLCedu and I am trying to send, for instance, 1 to out 2. And here we see that the red LED is lit on. If we are sending 0, then now it's off. This is just bit by bit. If we want to send 4 bits at the same time, now I'm sending 4 bits, 4 ones, and now I'm sending 4 zeros. Here we see just the VU meter. Now the needle is marking 5 volts. Now I am about to send 7 volts. And you see that the needle is marking 7 volts. And if we send 3 volts, now the needle is marking 3 volts. It is between 0 and 10 volts. And about the inputs, we can read just the input, digital inputs. And now we see 4 zeros. And in this particular case, that is connected to the bit 1, there is here a 0. Now I'm about to press the button. And pressing this button, now I am just clicking on the in bits. We see this one, bit 1, and now again I am pressing this, and I see that the value is 1, and if I am not pressing it, it is 0. Okay, and the analog input, now I am reading 5.35, and now I am moving the potentiometer a little bit, and I see that the value has changed. Now it's time for questions. If you want to do some questions.
Thank you. I have a nerdy little complaint. The thing that you labeled the VU meter looks to me like a linear scale, right? It's a linear 0 to 10 volts.
Yeah.
So it's not a VU meter because those are logarithmic.
Okay.
Just a meter.
Thank you very much.
European standard for what a VU meter is.
Okay, thanks for the nerdy remark. Is there any other nerdy remark or a question? Okay, Alex?
I was wondering, along with having it that they are able to get back readings, were you thinking of adding in something to simplify pushing firmware directly to the system so that people would be able to program it using blocks also?
If I understand, you are talking about to put a snap inside the system?
Not to put snap in, but for example, you could have it that you would build out a long series of strings using blocks. So you could have some code pushing to the unit itself, because it is also, how do the students program the system? Because I understand that the block, like this is what you have here is meant to take readings from your system, but where do they do the coding of the system itself?
Okay, the students now, this system is just in a vocational training school here in Barcelona, just the biggest one, Escola del Treball, and the students start to use this using Snap. And then, because every PLCedu has a different MAC number, the students can use this from the cloud, and then they are controlling this just to get the basics. Once they are able to use Snap and control and read and write to the PLCedu, they use Python. There is just a public library. There is in the GitHub. In fact, you can see that in the presentation. And then just importing the Python library on the Raspberry Pi, they are able to read and write digital and analog inputs and outputs. That's the answer to your question?
Yeah. Yes,
and then you have a tether.
that's what I was wondering
Okay,
about.
so Bernard is just saying that you can also program it in Snap
Or-
tethered to your computer.
Yeah, and if you want to have it so that it was untethered, has anyone thought about doing some of the primitive, sorry, microphone.
If you want to get to look at the camera.
Oh, yeah. Have you thought about having it that you would have some of the Python available as blocks that you would push so as to ease students into going over to Python if they don't already have a background in it?
I don't think that exactly, but the names and the parameters of the Python functions are the same than in Snap, are exactly the same. Then the translation could do is really easy to do. For instance, here you can see this is just an analog output. You have this parameter, that is the channel, and this is the voltage. Here in Python, you have here the channel and the voltage, and then the function, Python function, is A out, and it's just the same. The first parameter is the channel, and the second one is the value. Okay, and it's the same with the rest of the blocks. A is just the same. You are passing the channel, or here, for instance, you are getting the 4 bits, or here you are getting the video you want. It's just exactly corresponds the same, the Python function than the Snap function.